everyone, my name is Atharva Kale and my teammate is Tenzin Shenyen. And in this talk, we'll be presenting our work exploring how two fundamentally different AI strategies, namely reinforcement learning and neuroevolution, perform on the classical game of Flappy Bird. The goal was to basically understand the strengths and trade-offs of each method. We have compared the algorithms, examined key research papers behind them, and evaluated the performances of the game to draw meaningful insights. Now, the Flappy Bird is it's a different, deceptively simple yet addictive mobile game where a bird must continuously fly through gaps between vertically stacked pipes, and the controls are quite minimal, wherein the player taps to make the bird jump and gravity pulls it down otherwise. What makes this game an excellent candidate for AI experiments is that it has no fixed goal, and only the real challenge is of surviving longer. There are delayed rewards, no explicit instructions, and the game requires real-time decision making under uncertainty. And because of this, it has become a popular test bed for evaluating AI agents as well. Now, the main real challenge with Flappy Bird lies in its nature of its dynamics, wherein there is no definitive end state or reward at the finish line, and survival is the only goal. The game has also delayed and sparse rewards, making it hard to learn patterns. Also, to add on to that fact, the bird must also learn from evaluating and repeated failures to improve, which is the hallmark of trial and error based learning. And finally, it's fast paced, that is, split second decisions determine success or failures. And these overall factors make it a strong candidate for testing both reinforcement learning and evolutionary AI strategies. Now, talking about the AI algorithms we've been comparing, uh, in our study, we have compared two models, broad AI paradigms, including reinforcement learning and neural evolution. And let's begin with the first one. RL basically mimics how humans learn from experiences. The agent interacts with an environment, taking actions, receiving rewards, and trying to maximize its cumulative future rewards. The core idea here is the policy, which maps states of the environment to actions. On the other hand, Neuroevolution takes a bio-inspired approach, where instead of relying on gradients or backpropagation, it uses genetic algorithms to evolve the neural network's structure and weights over generations. Like nature, neural evolution uses selection, mutation, and crossover to gradually improve a population of neural network agents. Now, while talking about the survey we have conducted for both of these papers, we went through the breakthrough in reinforcement learning, deep learning, and neural evolution. Reinforcement learning was basically formalized using state action reward frameworks, introducing core methods like Q-learning and SARSA in one of these papers. Along with that, some papers talked about deep Q networks, combining neural networks with RL to master video games from raw pixels, and some talked about a hybrid RL system, which was developed that used tree search and deep learning to beat human champions in the game Go. In the computer vision part of things, a deep CNN architecture improved image classification using GPU trading and dropout. Along with that, in some of the papers, transformers revolutionized natural language processing with self-attention mechanisms. And finally, evolutionary algorithms were shown to evolve both neural network structures and behaviors without gradients, proving effective in dynamic environments in some of the papers we surveyed. Now, talking about the first paper, which basically focused on RL or reinforcement learning, we'll zoom into how the model of this paper is like distributed and used, and it basically adopts a Q-learning approach, wherein the bird's current state is represented using three variables. One of them includes dx, which is the horizontal distance to the next pipe, dy, vertical distance to the pipe's cap, and Vy, which is the bird's vertical velocity. Along with that, the available actions are quite simple and binary. That is, one can either jump or do nothing and fall. Along with that, the reward function is also very straightforward, wherein we get +1 for surveying a frame and -100 for crashing into a pipe. Now, talking about the learning details, these include the key values or action value functions representing the expected total reward an agent can obtain by taking a specific action in a given state and then following the optimal policy afterwards. In simpler terms, they help the agent evaluate how good a model is or move is in a particular situation, and the agent updates these values over time to learn which actions lead to long-term success. And here, so forth, the Q values are updated using a modified Bellman equation with a learning rate of zero point 0.7 and 1. The model was trained over 1,500 episodes for tuning and then evaluated on 20,000 episodes and the more performance stabilized after about 1,000 episodes, with the final average score achieved was about 111.3, with the best running score of 245, which is not bad for a simple tabular method with no neural net involved. Now, further, I'd like on to pass on the presentation to Tenzin.
Hi everyone, I'm Tenzin. Let me start by talking on neuroevolution model overview. So the approach here, like neuroevolution using genetics algorithm. So both the paper one and paper two applies genetic algorithms to evolve neural networks for Flappy Bird instead of using the back propagation one, which we're like taught in class. Each bird is a simple neural network. Its fitness is determined by the game score, like how far it goes before hitting an obstacle. So the key steps here are initialization. Um, we start with the random neural networks, evolution, evaluation. Each bird plays the game. Fitness is based on score, selection. Top performing networks are chosen, crossover and mutation. So new networks are created by combining and randomly altering like parent networks and replacing these offspring form the next generation, right? And then repeat. So this cycle continues until performance is satisfactory. So the goal here is to evolve high performing agents through a population based search process. So if you look at the table, right, any neuroevolution 1 and neuroevolution 2, like both are like the same model, but like the key differences here are in its architecture, population, the hyperparameter tuning. So, so if you look at the input, right, the paper one just uses the distance to the next pipe and vertical velocity, and the paper two only uses distance to the gap, right? And if you look at the network architecture, the first paper uses three-layer network layer with three input and four hidden layers, whereas in the second paper, like three-layer network with two inputs and a hidden size varies from 1 to 20, like 1, 5, 10, 15, 20, and it has found that five is the best performing one. So the population size variable for the first paper, like 550 to 500, and found out best at 200. But in the second paper, it's just fixed at 10. And mutation probability, like tuned between 0.3 to 0.9, found best at 0.3. Paper two is just fixed at 2. Selection method, uh, fitness function, mutation target, and termination. There are like a little bit of you can just have a look at the table. So if you look at the performance comparison between the RL and NE from the paper one, right? So if you just can have a look at the table, you can see the average score of RL around like 110, and for NE, it's like average score is around 29,000. And if you look at the best score, RL is like 245 and NE is around 150K. So the key insights here is like NE achieved much higher peak scores with like more variance, but RL was more consistent but could not reach high scores like NE. If you talk about like key differences in the setup, uh, RL actually used a fixed Q table, like there is no neural network. It's like Q learning. Simpler, more stable, but it's kind of limited in performance. Whereas in NE, used neural networks with tuned hyperparameters. It covered a wider search space, allowing like better exploration. And if you think about the training time, any in paper one ran for like a large number of generations, giving it like more time to evolve stronger agents. Okay. So which approach performs better, right? So let me just reiterate once again, like neuroevolution, you see the best score, you see the average score, much higher performance compared to Arnold's best of like 245 and average of 111. So the strengths are like for any explores a wider solution space and like more adaptable through mutation and population diversity and better at escaping like local optima. So for the reinforcement learning, it's like more stable and consistent once trained, easier to understand and implement due to its Q-table approach. However, it struggles with complex, like dynamic environments like Flappy Bird. So a short conclusion here is like NE is more effective for this game, just thanks to its like exploratory power and adaptability. Limitations in the comparison, like if you think about the training budget, RL has had like 20,000 episodes, but But if you think about any in paper two had like fewer generations, and any and paper one actually had a good number of generations, but directly comparing them like from paper one and paper two, like there is like a huge generational gap. So if you look at the network design, like any in paper one use fixed four neuron hidden layer, but in the paper two is tested with multiple sites and found five neurons best, right? Hyperparameters, any has more had any actually had more tuning like mutation rate, population size, while RL use like fixed parameters, right? Set of differences like variations in experimental design make make direct comparison not fully fair. So a quick takeaway: while like any outperforms RL in like raw scores, right, the results should be interpreted carefully due to like different setup and tuning levels. Uh, so uh, a quick conclusion, right? Neuroevolution performs better in games like Flappy Bird, where exploration and adaptability are the key. Reinforcement learning offers more stability, but it's limited by fixed truth table policies. Paper one set up four hidden neuron and tuned population helped Annie achieve very high scores, right? Uh, Overall, the results show the value of flexible learning in dynamic, unpredictable environments. The key takeaway here are the Annie's population-based search allows for better exploration for solutions exploration of solutions. RL might need more tuning to avoid getting stuck in local optima because differences in experimental setup like network size, training time, tuning can heavily impact results. So yes, these are like a few key takeaways here. Right. Thank you for your time and